So here's how I think I'm going to teach electric fields this year to AP Physics 2. We're going to start off with this picture here. We've got the gravitational field lines on the Earth when we approximate the Earth as being flat. Right? The Earth is not flat. I feel the need to emphasize that in today's day and age. But since we are like ants relative to the size of the Earth, it looks relatively flat to us, and to a good approximation, the gravitational field above the Earth, at least around our human heights, is approximately uniform as a result. And the uniform value it has is 9.8 newtons per kilogram. And then we want to ask, how do we get that? How might we get this number? One option is we can grab ourselves a spring scale. Let me grab the other one, actually. It'll have better contrast against the whiteboard. And we can grab ourselves a 5 kilogram object. And if we place this 5 kilogram object on this spring scale and we measure however much force it gets pulled down by this gravitational field, well, then we'll end up with the gravitational force on this 5 kilogram object. We would measure, we'll say, let's see, G is, let's call this 10 for simplicity. The gravitational force would be 50 newtons of force that we would measure. If we swap out this 5 kilogram mass with a 10 kilogram mass, and we grab our spring scale and we measure how much pulling down there is, we would measure the gravitational force now on this mass is twice as much. It is, what is that? 100 newtons. 10 kilograms times 10 newtons per kilogram, 100 newtons of gravitational force. If we swap out our 10 kilogram object for a 15 kilogram object, we use the spring scale to measure how much it gets pulled down in that field. Well, what? We would measure the gravitational force to be 150 newtons. That's what it means to have a gravitational force of 10 newtons per kilogram. For each kilogram of mass I have, the gravitational force will be 10 newtons of force. So I have 15 kilograms here. That gives me 150 newtons of gravitational force on that object. All right, so no big deal. But now what if we hop on our spaceship and we leave Earth and we land on the surface of planet X? And as the intrepid scientists that we are, we want to know what the gravitational field strength of this planet is. What would we do to figure out the gravitational field of planet X? How many newtons per kilogram is that field? A property that describes just this planet. Well, I'd probably take my same 5 kilogram object and my same spring scale and measure how much it gets pulled down in this field. And let's say the spring scale gives me a measurement of, let's say it gives me a measurement of 15 newtons of force. Well, then to quantify the property of this planet, I would get G is that gravitational force divided by the mass, or that 15 newtons divided by my 5 kilograms. And I would end up with a gravitational field strength of 3 newtons per kilogram. All right, that all seems well and good. But we would probably want to do a little bit better if we were being careful as scientists. We would want not one measurement, but many. So we might grab our 10 kilogram object and we would check, does the gravitational force measure 30 newtons? And if it does, this seems like a pretty good, good value for the gravitational field of this Earth. And if we were really wanting to be careful about it, we might draw a graph where we would plot the gravitational force that we're measuring against the mass of whichever of these guys we're throwing in that gravitational field. And if we did that, we would end up with a line whose slope on this planet X was equal to 3 newtons per kilogram. some terminology here. We're trying to define the gravitational field of just the planet, but to do that, we need a few test masses. We need to use these guys and measure that force, because all forces are an interaction between two objects, but we want something that just characterizes the planet regardless of which test object I use. So I can't say with any certainty how much force another object will feel on that planet, but I can say how much force it will feel per kilogram, and that still seems pretty good. And that's a number that just quantifies planet X. All right, folks. Now what if, let me clean this up a little bit here. We're going to swap out this idea of a gravitational field with something different. We're now going to replace this gravitational field with an electric field, a new concept to us. And we are going to replace the surface of our planets with a piece of metal that is infinitely long. Obviously, we can't have a piece of metal that's truly infinite, but so long as our objects are very close relative to the size of the plate, then an infinitely large plate is just as good of an approximation as a flat, infinitely long Earth. And we know that since there's negative charges on this plate, if I grabbed myself a positive 3 Coulomb charge, so this isn't the mass of the object anymore, this is now the charge of the object, then it will be attracted to this infinite plate. And in fact, it will be attracted with a constant electric force. So this object will accelerate downward at a constant rate. But let's say we want to quantify something about the space around this plate. We want to quantify the strength of this field. How might we do that? Well, I could grab my spring scale again, and I could measure how much force this guy feels in that electric field. And so maybe we measure something like the electric force on this charged object attracted to this infinitely long plate ends up being 21 newtons. And so a 3 Coulomb object is feeling 21 newtons of force. That must mean that the electric field, we'll use capital E for that, is equal to the electric force divided by the charge of that test object, we'll call Q naught, which will in this case equal 21 newtons per 3 coulombs, or 7, not newtons per kilogram anymore, because we're not talking about gravity, but newtons per coulomb, because we're talking about the electric force. Take out this charge. I would want to be careful, right? One charge isn't enough. So let's grab ourselves another one. Maybe this 11 Coulomb charge. We grab ourselves our spring scale to measure how much attractive force there is between these two objects. And we would probably measure something like 77 coulombs, because the electric force, or the electric field, is 7 newtons per coulomb. So we take this 7 coulombs, or newtons per coulomb, multiply by the 11 coulombs, and you would get 77, newtons of force there. All right, so I think we have developed the analogy between the gravitational field and the electric field. I want to showcase one thing that's going to be different. For gravitational fields, the force that you experience will always be in the direction of these field lines, right? Things are always attractive through gravity. But if I grab myself a negative 2 Coulomb charge here, it won't be attracted to that negative plate. It would be repelled. And so it's going to feel a force in that direction. So it's going to feel an electric force of 2 coulombs times 7 newtons per coulomb would be 14 newtons of force in the positive direction. So the thing that differentiates electric fields from gravitational fields is that in a gravitational field, all objects will follow the direction of the field lines, but in an electric field, only positive test charges will be accelerated along the field lines, and negative charges will be accelerated in the opposite direction of the field lines. Now, one point I want to emphasize, I've mentioned it, but I want to emphasize it once more before we conclude, is that we were trying to characterize the space just around this plate. The 7 newtons per coulomb describes what will happen if you put a test object here. There isn't anything there right now. There doesn't need to be anything. But in order to measure it, you do need to throw in some test charges. And if you do that, then you can measure what's going on for this space. All right, that's my quick summary on electric field introductions.